Hi friends, my name is Murad Waili. In this video, I'll try to explain the mathematical approach to solve the problem 869 reordered power of 2 from leetcode. You are given an integer n. We reorder the digits in any order, including the original order, such that the leading digit is not zero. Return true if and only if we can do this so that the result number is a power of 2. If we take some examples here, for example, n is equal to 16. 16 is a power of 2 such as 2 power 4 is equal to 16. As we see here in this list of powers of 2. Another example, n is equal, for example, 9064. This number by itself is not a power of 2, as we see here. It doesn't exist. It's 4 digits here, and it doesn't exist here. But if we rearrange the digits of n, we can have 4,000, 96, which is a power of 2. So we say 2 for this n. Then another example, the last example, n is equal, for example, to, I don't know, for example, 8,000, well, 8,123. This number, this n, it cannot be rearranged to get a power of 2. Not this number or this number is not a power of 2. This number it also is not a power of 2, and so on. We say false here. The approach, the mathematical approach of this problem, one of the mathematical approach, maybe there's another smarter solution. I don't know exactly. Let's take an example here. For example, n is equal to 9,064. As you see here, n contains 4 digits. So the first subtask, we have to compute x, which is the number of digits of n. Let's call this x is equal to 4. From this x, can we determine or compute the range of all the power of 2's, all the powers of 2 that contains 4 digits, all the power of 2. This range here. Let's call this number k1. K1 is equal to 10 here. and K2 is equal to 13. Why this range? Because n has or have 4 digits here. So we're going to search if there is a power of n that contains 4 digits has have the same digits such n. For example, here 2 power 10 is 1024. 1024 does not have the same digits as n. So we jump to 11. 2 power 11 is 2048. Does not have the same digits as n. N is equal to 12. 2 power 12 is equal to 4096. 4096 has the same digits as n. We have 4, we have 4, we have 0, we have 9, and we have 6. So we can say true here for this. How to get this range from K1 to K2? We have some subtasks to do here. The first one, as I said, we compute the number of digits of n. Then compute a number a or integer a, which is the lowest integer that contains x digits. Then compute an integer b, which is the greatest integer that contains x digits. Compute k1, which is the lowest exponent to get a, such as 2 power k1 is greater or equal to a. And compute k2, which is the largest exponent, to get b, such as 2 power k2 is less or equal to b. Then, for each exponent I from k1 to k2, return true if there is an integer p equal to 2 power I, which have the same digits as n, false otherwise. How to compute x, which is the number of digits of n? Our number n here, for example, this example, we can write it this way, is equal 9.046 times 10 power 3. Any number n, we can write it is equal to k times 10 power x minus 1, which x is the number of days of n. So the natural logarithm of n is equal the natural logarithm of k times 10x minus 1, 10 power x minus 1. This one. We can say also that the natural logarithm of n is equal to the natural logarithm of k plus the natural logarithm of 10 power x minus 1. As we know here, that logarithm of a times b is equal natural logarithm of a plus natural logarithm of b. Which is equal the natural logarithm of n is equal to the natural logarithm of k plus x minus 1 times natural logarithm of 10. This property comes from natural logarithm of a power b is equal to b times natural logarithm of a. So x minus 1 is equal to natural logarithm of n minus natural logarithm of k over natural logarithm of 10. So x minus 1 is equal to logarithm by base 10 of n minus logarithm base 10 of k. So this is our first formula. We know that k is equal n over 10 power x minus 1. So um, the logarithm base 10 of n minus the logarithm base 10 of k is equal to logarithm base 10 of n minus logarithm by base 10 of n over 10 power x minus 1. We can conclude from this formula that we can get this equality here. Logarithm base 10 of n minus logarithm base 10 of n plus x minus 1 times logarithm base 10, the logarithm, natural logarithm. Here this is not the natural logarithm, sorry, is logarithm base 10 here of 10, here log base 10, which is this gave me 0 plus x minus 1 is equal x minus 1 times 1. This give me 1 here. The formula is correct here. X minus 1 is equal to x minus 1. So if log base 10 of n minus log base 10 of k is equal to x minus 1, this one is equal to x minus 1, we can conclude that logarithm base 10 of n is between x minus 1 and x. So x, which is the number of digits of n, is equal to the integer part of logarithm base 10 of n plus 1. This formula give me the number of digits of an integer n such that n is positive here, must be positive. If n is negative, which is not our case here, but for your information, we use the floor. X is equal to floor logarithm base 10 of n plus 1. Okay. How to calculate the a, which is the lowest integer that contains x digits? A is equal to 10 power x minus 1, which is above here. If n contains 4 digits, the lowest integer that contains 4 digits is 1000. So 10 times 3, 3 is 4 minus 1. But to compute a is here, you can use the power function or make your function as you want, you guys. For me, I'm going to use a mathematical approach, as I said. So here, natural logarithm of a is equal x minus 1 natural logarithm of 10. The e number here, the exponential of natural logarithm of a is equal the exponential of x minus 1 natural logarithm of 10. Here it will give me a because these two functions, the natural logarithm is the f minus 1 or the inverse of the function e. So a is equal to exponential of x minus 1 times natural logarithm of 10. B is easy to compute it. It's the largest or the greatest integer that contains x digits, which is a times 10 minus 1. If n contains 4 digits, for example, a is equal to 1000, and b, which is the largest number that contains 4 digits, integer, which is this number. How to obtain this number? Multiply I by 10 and subtract 1. How to compute k1, which is the lowest exponent to get a, such as 2 power k1 is greater or less, is greater or equal to a. So a is less or equal to 2 power k1. Natural logarithm of a is also less or equal to k1 times natural logarithm of 2. So k1 here is greater or equal to natural logarithm of a over natural logarithm of 2, which is k1 is greater or equal to logarithm base 2 of a. So k1 is the ceiling of this result, natural logarithm base 2 of compute the ceiling here. Same idea for b. b is greater or equal to 2 power k2. We can conclude here that k2 is equal to the floor of logarithm base 2 of b. Now for each exponent a from exponent I from k1 to k2, return true if there is an integer b which is equal to 2 power I, which is have the same digits as n, false otherwise. Let's take an example very quickly here. For example, n is equal to 6409. X is equal to 4 digits. A is equal to 1000. B is equal to 9999. K1 is equal to the ceiling of log base 2 of 1000, which is equal, we compute it using a calculator, log 2 of 1000 is equal to 9. The ceiling is equal to 10. So here K1 is equal to 10. For K2, K2 is equal to the floor of log base 2 of B, which is 9999, which is equal to here. 18.28, the floor is equal to 30. So from 2 times k1 to 2 times k2, we're going to look for an integer. If we have an integer, a result which is have the same digits as n. 2 power in this range from 10 to 30. It's a smart brute force. 2 times 10, 2 power 10, sorry, is equal to this number, 1024. Doesn't have the same digits as n. 11, not. 12, yes. So we turn to for this n here. Very quick, another example. Here, let's take 5 digit, for example, here. N is equal to, or 6 digit, for example, here, 1, 6, 2, 1, 6, 1, 6, 2, 2, 4, 4. X is equal to 5. X, number of digits of n is equal to 5. A is equal to 10 times 4, 10 power 4, equal to 10,000. B is equal to this number, the greatest number that contains 5 digits. Log 10,000 is equal to, log base 2 is equal to 13. The ceiling is 14. Okay, it's correct. 14. Log the b, log base 2 of b, here. The floor here is 16. So we're going to search, to look for in this range from 14 to 14, 5 digits or 6 digits. Sorry, 6 digits we have here. So sorry for this guy. 6 digits. Here we have 10,000. Here we have this 100,000 here. So here we're going to have 16. The floor is 17 here, and the ceiling is 17 of this result, and the other one B, the floor is 90. So for 6 digits, we're going to look from 17 to 90, and this one. Okay, it's correct. This one does not have the same digits. This one does, so we turn to here. If we have another number of n, for example, this one, if we have, for example, 8 here, we turn false because we do not have, this one does not have the same digits as this. Same for this, 2 power 18. Same for 2 power 19. So we return false. How to know if two numbers have the same digits? We can use this approach. It's a very known approach here. Simple. We initialize an array that contains tens elements and integer here to 0, from 0 to 9, or 0. For example, if we want to know if p and n have the same digit or not, we're going to use two counters, a and j. First of all, a and j contains the same value. Initialize a and j, a to p, for example, and j to n, and g to n, sorry, j, sorry, 15 here. Okay. Now we're gonna take digit by digit from a and g. We take digit by digit from a and g. 5. Look for 5 here. Add 1 here. We add 1 here. We're going to add 1 for for each digit of I, and reduce 1, subtract 1 from each digit of j. 6 here. 6, it will be 0 minus 1, it will be minus 1. Then we go to here we have 1 and 5. 1 here, we add 1 here, become 1, and we reduce 1 from 5, it will be 0. We reduce a and g, 6 and 0. 6 here we add 1, so it became minus 1 plus 1 became 0 here, and 0 here for j, it will be minus 1. 6, 9 and 4. 9 here, we add 1 here, reduce 1 in 4, index 4 here, be minus 1. 1 and 0. For 0 here, we add 1, minus 1 plus 1, it will be 0. And at index 1, we have 1. 1 minus 1, it will be 0 too. We reduce a and g. The last digits, 4, minus 1 plus 1, it will be 0. And 9, at 9 we have 1, 1 minus 1, it will be 0. As you see here, we have all the digits at 0 here, which means reduce here, it became a became 0, j became 0, and I became 0 here. But the most important thing here, that all the digits are 0, which means the main idea here, if we add 1 to the each digit of I and reduce 1 from each digit of j, if the digit exists in A and J, it will become 0. Plus 1, minus 1 for each digit. We have 0 for each digit and for each index in the table counts here. The code, first of all, if n is equal to 1, return true. It's a special case. Compute x using the formula as we have seen. Compute a, which is the exponential of x minus 1 times log the natural logarithm of 10. Compute b, compute k1, compute k2, and do a smart brute force from k1 to k2. Compute the power 2 power I and check if we have the same digits between p and n. This is the function. Initialize a table counts of 10 digits from 0 to 9 to 0. We iterate over each digit in I and j. I at first equal to b and j is equal to n. If a and j both are different of 0, reduce I, reduce j, then for each digit of I add 1, for each digit of j reduce 1, then check if we have a digit that is different than 0, return false, otherwise return true. Let's submit this code. Okay, as you see, it is accepted and beat 1000% of CP submissions. Thank you guys for watching, and see you soon.